Hello, ladies and gentlemen, and welcome to Mr. Saucedo's YouTube videos. Today we're going to be looking at how you can write equilibrium expressions for various chemical reactions. So we talked about what equilibrium is, and here is kind of a more formalized definition. So the concept of equilibrium was derived from experimental data collected by Goldberg and Vogt in 1864. And so instead of calling it equilibrium, they called it the law of mass action. And so here's a generic chemical equation. So I have J, K, M, and N, and I have capital A, capital B, C, and D. Now, it doesn't matter. These here, the J, K, M, and N, are coefficients. They can be any whole number, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Keep going. A, B, C, and D, those are any reactants. So these are reactants on this side, and these are products on that side. Okay? Again, they can be anything. There doesn't even have to be 2 and 2. There can be 1 on this side, and there can be 2 on this side, or there can be 10 on this side and only 1 on this side. It really doesn't matter. Okay, so if you are going to forget that, you might want to write that down. So these are the chemicals. These are our coefficients in our nice balanced chemical equation. So yeah, you got to be able to balance equations still. So their law of mass action was derived to be this. So K, which we're calling the equilibrium constant, equals products over reactants. So they found that when you take C and D and you multiply them together, and you raise them to the powers of the balanced equation, and then you divide by your reactants using the same method. So you take your amounts, you multiply them together, but you raise them to their respective powers. That gives you the equilibrium for that reaction. Okay? And so when you numerically calculate this, that gives you what we call a K value, which I just said is the equilibrium constant. So how do we write equilibrium expressions? It's kind of easy, right? All you got to do is, if you have a balanced equation, follow the format. So how would I write the equilibrium expression for this? These are my products. These are my coefficients. These are my reactants. These are my coefficients. And so K equals products over reactants. These are my products. They are raised to their correct powers. These are my reactants. They are also raised to their correct powers. Simple as that. Now, K changes, though, with temperature. So if you're conducting this experiment, you're like, okay, well, hey, I have a K value. That's fine, but it only works at a certain temperature. If you increase or decrease the temperature, the K value will change. And also, in equilibrium expressions, only gases and aqueous solutions are included. What that means is solids, if there are any solids or pure liquids, they have a constant concentration and they are not included in that reaction. Okay? That doesn't mean they're not a part of this reaction at all. All that means is that they're not included when you're trying to find the equilibrium for that reaction. So here's another kind of little random fact here. Now, if everything is in the same phase, meaning, let's say all of them are gases or all of them are aqueous or something, that means that you have a homogeneous equilibrium. On the other hand, what if you have some solids, you have some liquids, you have some gases? That would be a heterogeneous equilibrium. Homogeneous meaning everything's the same. Heterogeneous meaning there's at least one thing that's different. So here we go, right? I've got H2O, I've got H2, I've got O2, but remember, always look at your actual, states of matter first. What would the K be for this reaction? Answer: K equals H2 squared times O2. Why didn't I include water? It's a liquid. Also, it is heterogeneous. I have gases and I have liquids, so it's heterogeneous. Next up, what about this one? Answer: those are my products. These are my reactants. Notice again, you're raising them to the correct powers. Heterogeneous or homogeneous? What do you think? Homogeneous. Next up, what do you think the equilibrium expression for this would be? Answer: just Cl2. Notice, liquid, solid, they don't matter. And it is definitely heterogeneous. I have solid, liquid, and gas all in that one reaction. What about this one? Answer: that is going to be my product. These are my reactants. I didn't include sugar because it is a solid in this situation, and that means that it's heterogeneous. I have solids and gases. What about this one? Answer: CO2. Again, these are solids, and so is it heterogeneous or homogeneous? Heterogeneous. This one. Next, okay, answer here. These are our products. These are our reactants. Yes, we include, our little charges and stuff, okay, but these are not raised to any power because there's no coefficient in front of any of them. Heterogeneous or homogeneous? Homogeneous. All right, now, if K is much greater than 1, then that means that the reaction is considered product favored. Okay? In other words, at equilibrium, mostly products will exist. If, on the other hand, the K value that you find is much smaller than 1, that means the reaction is reactant favored. That means at equilibrium, there will be more reactants. Why do you think that's the case? Any idea? Answer. K is products over reactants. So picture this. If this is a large number and this is a small number, K is going to be large. That means it's product favored. There are mostly products. On the other hand, what if this is a large number and this is a small number? Small over large number, this is going to be a really small number then, and that means there are mostly reactants. So